Today's lesson focuses on the ideal gas law. An ideal gas is a hypothetical gas. And even though it is a hypothetical gas, we do find that most of the gases that we use really do behave as this perfect ideal gas. And this is one that obeys all of the gas laws that we've mentioned. So Boyle's, Charles, Gay-Lussac law, perfectly under all conditions. And some extra properties would be that it wouldn't condense into a liquid when cooled, that graphs are all perfectly straight lines. For example, if there was a direct relationship between pressure and temperature, you would see perfectly straight lines. So this is sometimes hard to obtain under normal conditions, but real gases really do behave in this ideal way. There's sometimes some irregularities, but they have found that unless you are dealing with very low temperatures or very high pressures, the gases will all behave according to the gas laws. So just a reminder that an ideal gas will follow the following criteria or gas laws. So Boyle's law, that the volume is inversely proportional to the pressure, that the volume of a gas is directly proportional to its temperature. Gay-Lussac pressure of a gas is directly proportional to its temperature. And then lastly, the greater the amount of gas in moles, the greater the volume. In order to relate all four variables of an ideal gas together, we have a new formula called the ideal gas law. And this ideal gas law incorporates our four variables. So it incorporates pressure right here, it incorporates volume, it incorporates the amount of gas, which is moles, and it incorporates temperature. The only thing that it does not, or that is new in terms of what it incorporates, is a constant. So an ideal gas constant is what we need to bring in because we know that these four variables are proportional to each other. So when we know that pressure is proportional to volume, and that symbol is the symbol for proportional, or we know that the moles of a gas are proportional to the volume of a gas, in order to take those ideas and those variables and turn them into a mathematical equation, we need to incorporate a constant. This is basic mathematical science of chemistry and physics. So R is a gas constant, and it has a very specific value, and it has very specific units. So if you look here, you'll see that the unit is kilopascals times liters divided by moles Kelvin. And those are the units that we need for each of our variables. So now we have to have specific units. Okay, so we have to have our pressure in kilopascals. We have to have our volume in liters. We knew already that we would be dealing with moles, and we knew already that we would be dealing with Kelvin as the temperature because those are standard for gases. But now you have to have specific units for pressure and volume. So let's try an example with the ideal gas law. And here's a scenario. It says if 0.78 grams of hydrogen at 22 degrees C and 125 kPa is produced, what volume of hydrogen gas would be expected? So previously, when we looked at our gas laws, we were only looking at two variables at a time. Actually, when we were dealing with combined gas law, that had three variables, but we never incorporated amount of a gas. So now we will be bringing that in using the ideal gas law. And we know that the ideal gas law states PV equals nRT. So I need to figure out the moles of hydrogen first. They give me the mass, and this is an easy calculation. And remember that hydrogen is diatomic, and we need to do mass divided by the molar mass of it. So we're going to take 0.78 grams. We're going to divide by the molar mass of 202 grams per mole. And we get a mole value of 0.3861, I'll go to that, moles of hydrogen. Now we can take that mole value and we can put it into our ideal gas law, and we can rearrange to find volume. So if I want to solve for volume, I have to move pressure out of there. We're going to divide it out. And so we're going to set it up that the volume of hydrogen is equal to nRT divided by P. And we're going to start to sub in our values. Moles is 0.3861 mole. The constant, if you recall, 8.314. Now, to remember the units, because you got to put units in, I usually say the unit. So I usually say kPal over molk. Okay, kind of a silly thing. This is supposed to be kPa, but it's a way to remember the unit because there's 4 units there for the constant. So kPal over molk is usually how we write that. And I'm running out of room. I need a temperature as well. So I need 22 degrees C. We're going to add on 273 to that. That gives me 295 Kelvin. And then we're going to divide everything by the pressure. And I need it to be in kPa because of the gas constant unit. So we divide by 125 kPa. And this gives me a volume of, calculator gives me all kinds of decimals. What do I need? I need 2 sig figs because of the mass that's here. So we need 2 sig figs. So I'm going to be rounding to 7.6 liters. Let's try another one, or you can try it on your own and then come back and watch the video after. It says, what mass of neon gas should be introduced into an evacuated 0.88 liter tube? So that just means that there's nothing in this tube, like literally all the air molecules are out of it, to produce a pressure of 90 kPa at 30 degrees C. So this is, they're setting up a neon sign, okay? So when you see those neon signs, the open, for example, they're trying to set this up so that they know a pressure that's going to be applied to the glass. It won't bust it open when they plug it in. So we set up our ideal gas law. Okay, so PV equals nRT. They are asking us to solve for mass. I don't have mass in this formula, but I have moles. And once I know the moles, I can rearrange the moles and figure out the mass of neon that I would expect. So if I want to solve for moles, I got to take RT, bring it down, and set that up. So PV divided by RT. We're going to sub in what we know. So we know that it's 90 kPa, and that's the unit that I need. My volume is supposed to be in liters, and it is 0.88. And again, these units are specific because of the gas constant. So R is 8.314 kPal over molk. It works. Trust me, you're going to say it to yourself. And then you're going to multiply by the temperature. So I have 30 degrees. I'm going to add on 273. That gives me 303 Kelvin. So let's calculate our moles. So I am getting a value of 0.03144, I guess, I'll call it there, moles of neon. And then they ask us for the mass. So let's just quickly convert into a mass of neon. And we're going to take moles times the molar mass. So we take 0.03144 mole. And then we multiply by the molar mass of neon, which is 20.18 grams per mole. And then when we calculate this, we need to round to 2 sig figs. So I'm going to come up with a mass of 0.63 grams. Okay, give this one a try on your own. We need to calculate the molar mass in this particular question. So they give you your parameters here. They say calculate the molar mass. So you know you've got to solve for moles first and then rearrange to solve for molar mass. And be aware it's at STP. So at STP, you know those conditions of pressure and temperature. If you can't remember, look at the previous note. Make sure your units match the ideal gas constant, and then see if you can set up this gas and identify what the mystery gas is here. Come see me if you have any problems with this one. This last example that we'll do is an application of the ideal gas law. It's very, very common with gas chemistry to speak of gases in terms of their density, because we know that gases can be squeezed into any kind of space. So depending on the volume of your container and how much you put in, density is a very good way of relating and discussing these gases in terms of, you know, you're hitting two variables right off the bat, how much gas and then the volume of your container. So when they ask for density, we want to rearrange our ideal gas law to solve for mass over volume, right? So we know that density equals mass divided by volume. So if I could rearrange my ideal gas law for those two variables, then I'm solving for density. So how do we do that? So let's set this up. So we would do PV equals nRT. And I don't want moles because I need to get a mass value. So all I'm going to do is I'm going to rearrange and substitute mass divided by molar mass for moles. And then RT stays in the numerator. And I just simply extend that division line. And now instead of a mole value, I have mass over molar mass. It's the same thing. So what I want to do is I want to push my variables around so that I isolate mass over volume on one side of the equation. And this is an easy fix right here. I'm going to just substitute and swap those two around. And then I'm going to take RT and I'm going to move it to the other side. So let's first do the P and the molar mass swap, okay, which is going to give me mass over volume. Okay, so see what I did? I just took these two variables and I switched spots, times RT. And now I'm going to take RT and I'm going to bring it to the other side. So I end up with mass over volume, which is equal to density, equaling pressure times molar mass divided by RT. Now, you can memorize this formula if you want. I don't like memorizing things. I like to understand how stuff gets set up. So you can watch it again to see how we can rearrange that formula to solve for density. When we do, we now can substitute all of our variables or our data into our equation. So the density for carbon dioxide is equal to, again, pressure times molar mass divided by RT. And I know that the pressure at SATP is 100 kPa. The molar mass of carbon dioxide is 32 and 1201 is 44.01 grams per mole. And then R is always the same, 8.314 kilopascals liters over moles Kelvin. And then my temperature at SATP is 25 degrees. So remember, we got 100 kPa, got to know these. 25 degrees C plus 273, I get 298 Kelvin. And then we come up with our density value. Okay, so when I push everything into the calculator, I'm getting, again, a big value. Now, you don't have any data here, okay? So everything is based off of constants. So what do we do? I guess we're going to go with 3 sig figs. We're going to assume that that pressure and that temperature is in my 3 sig figs. So I'm going to round this to 1.78. And it is grams per liter, okay? Remember over here, we are solving for mass and volume is in liters. And that's how we would solve for density of gases.